When we think about reflections, we think about a mirror image. So for part A, we have the original parent function here, x squared. But notice that f of x equals negative x squared, making that leading coefficient negative, reflects this graph over the x-axis. Because now, if we did a t-table, for example, f of x equals negative x squared. If you plug in negative 2, negative 1, 0, 1, and 2, for example, we'll get negative of a negative 2 squared, which is negative 4. Negative of a negative 1 squared, which is negative 1. And again, you need to use, please excuse my dear Aunt Sally, meaning we need to do our parentheses and exponents first before we bring in that negative. So everything in here, since it's being squared, would be positive, but times that negative on the outside would make it negative. All right, and then we have negative 0 squared. 0 is neither negative or positive, so we just put 0. Negative 1 squared would be negative 1, and negative 2 squared would be negative 4. So those plots, negative, let's plot that. Negative 2, negative 4, negative 2, negative 2, negative 4. So now 1, 2, 3, 4. Notice we're down here. All right, we're down here. Negative 1, negative 1, negative 1, negative 1. So you see where it's getting its shape, why it reflected over the x-axis. If you put a negative in the very front for the leading coefficient. All right, now this one, we have the square root function. Normally the square root function, as you can see, is going to the right. We have described it in the past as rainbow, right? Like a rainbow is going to the right normally. But in this case, notice it reflected over the y-axis. And why is that? Because the other one reflected over the x-axis. But notice this is like on the inside of the function. So this is a reflection with respect to the y-axis instead of the x-axis. This one was a reflection with respect to the x-axis. So I would suggest you use Desmos to kind of play around with it. See what would happen if you plug in a negative on the outside, for example. So let's do that. Let's go to Desmos really quickly. So our original parent function, let's just do the original parent function. F of x, and you really don't have to put f of x in here. I'm doing it just to start it off. But you really don't have to put that part in Desmos. It will work without it. But notice, okay, so that's what we're familiar with. But if we plug in, and what if we put square root negative x, it goes there. But what if the negative was on the very outside? What do you think would have happened if it was on the outside of the function instead? So that was in green is a reflection across the x-axis. What's in green is a reflection across the x-axis. What's in blue is a reflection across the y-axis. And what if we did both? Right? look at what would happen if we did both. Notice it's a reflection across the origin. Well, reflection across X and Y. All right. So play around in Desmos to get an idea of what happens when you put a negative in certain spots. Okay, so what about, which is interesting, if we put square root of x plus 3, all right? Notice that is the same thing as, for something like this, I would want you to factor out the negative. So you have an indication of what's really going on. So I'll factor it out like this, x minus 3. All right, and I'll look at that. See how it was the same as the blue? All right, so if I took that off, you see the blue. So I'm going to put the black on. It's the same exact one. And notice it went to the right 3 units. It still was a reflection across the y-axis, but it went to the right. So I like, when it looks like this, I like factoring out to determine what is the translation or transformation here. There was a horizontal shift to the right 3 units, but it still was a reflection across the y-axis because of that negative in the very front. So play around with Desmos. That's just my little tip. If it looks like something like this on the inside of a function, factor out the negative to determine what it really is doing. Now let's talk about vertical stretching and vertical shrinking. So this is what I'm pretty much going to test you on, vertical stretching, vertical shrinking, even though it says a vertical stretch has comparisons to a horizontal shrink. So basically they're saying they're very similar, and a vertical shrink has comparisons to a horizontal stretch. I'm going to only teach you this, and I'm going to test you on vertical stretching and vertical shrinking. So it says use the graph of f of x equals x squared to sketch the graph of each function. G of x equals 3x squared and h of x equals 1/3 x squared. Notice that the original parent function is pointing to it is in black. That's where it lives normally. But how does this 3 affect the shape of the graph? Notice that's the one in pink, right? So notice I would say it's getting skinnier. When you say it's getting skinnier? So it is a vertical stretch, actually. So think about stretching Play-Doh vertically. If you stretch Play-Doh vertically, it gets skinnier, right? Or let's say that you are, for some reason, you became taller, but you stayed the same weight, but you got taller. You would appear skinnier. All right, you would appear skinnier. Okay, let's look at 1/3 x squared. How did that affect the graph? I would describe that as it got wider, right? It got wider. That's an example of vertical shrink, right? Vertical shrink. If it gets skinnier, it's vertical stretch. If it gets wider, it's vertical shrink. So here's what you need to know to sum it all up. So write this in your notes. So we have a situation like, let's just write out the general form of a quadratic, ax squared, right? So if, when your a is greater than 1, like this one, a here is 3, okay? When it's greater than 1, the graph is a vertical, what do you think I'm going to say? Stretch. When a is between 0 and 1. The graph, what do you think it is? Is a vertical shrink. Vertical stretch, meaning we are getting skinnier. Vertical shrink, meaning we're getting wider and fatter. All right? So that's what you need to know. Let's just go over a few examples to see if you got it. So we're going to start off slow here. Let's say I want you to identify parent function, the one parent function. 2, I want you to identify the shape and the shifting or the translations or transformations. All of it means the same. All right, so if we had f of x equals the square root of x plus 3, what is the parent function? Parent function is f of x equals the square root of x. It is the square root function. How does it look? Well, the shape is normally like this, like the rainbow, right? It's going off to the right like that normally. However, we have some shifting going on. All right, we have some shifting. So what is the shifting? We have a do we have a horizontal shift or a vertical shift? We actually have a horizontal shift. Where though? Where? From the original, where are we going? Horizontal shift to the left, 3 units. So if you said that, great job. We're gonna go to the left. So I'm taking that little point right there. I'm going to the left. 1, 2, 3 units. And we're going to draw the same thing. We're just moving to the left 3 units. So this is the new function or child function, offspring function, f of x equals the square root of x plus 3. What about f of x equals x squared minus 5? What is the parent function? The parent function is the quadratic function. F of x equals x squared. How does it look? The shape looks like a U. Like that, right? A parabola. However, we have some shifting. Is this vertical shifting or is this horizontal shifting? Notice we have the parent function here, plus or minus c. So if you have some plus or minus c, that is vertical shifting. Vertical shift where? Exactly where you think it should go for vertical shifting. Down 5 units. So I'm taking that center, going down 2, 1, 2, 3, 4, 5. We're here. So our new function is down here. Same shape though. What about f of x equals x minus 2 cubed? What is the parent function? The parent function is the cubic function. F of x equals x cubed. What is the shape? It looks like a snake. It's going to do something like this. However, do we have vertical shifting or horizontal shifting? This is enclosed inside of the function. Therefore, this is horizontal shifting. It goes opposite of what you think, to the right 2 units. So I'm taking that center, that's my anchor point, and I'm moving it to the right 2 units. So we're over here instead. Now, we're over here doing the same thing. So we're going to erase this one in pink. All right. What about f of x equals the absolute value of x plus 3? Well, parent function is the absolute value function. F of x equals the absolute value of x. What is the shape of that? So memorize the shapes of these parent functions. Is a V shape. However, is this vertical shifting or horizontal shifting? Well, we have a parent function plus or minus c. So you have that c on the outside, not enclosed this time. So we have vertical shifting. Where though? Vertical shift up 3 units. So we take that middle part, we go up 1, 2, 3. We're here instead. All right, what about if I gave you f of x equals 5 times the absolute value of x? 5 times. So we don't have a plus c on the outside. We have 5 times. So again, we go back up here when we have an a times the parent function. When the a is greater than 1, like 5, the graph is a vertical stretch. What does it mean? It gets skinnier than the original. So let's say the original was this, for example. Then our 5 times the absolute value function would get skinnier, right? And also, if we had f of x equals 1/2 absolute value of x, then if our original was this, then our offspring function or child function would get wider because that 1/2 is a number between 0 and 1. 0.5 is a number between 0 and 1. Therefore, we have vertical shrink, which means that our function looks wider, almost like pressing down Play-Doh, compressing it, then it kind of oozes out wider. So hopefully this helps you with transformations of functions.